Well, thank you, Adrian. It is an exciting time to be a part of Kepler. We launched our mission just a little over a year ago. In fact, today is the anniversary of our start of our science operations. A year ago, we started science observations. So we're bringing down data every month, and we are looking for planets very hard. And we've right now are at the start of the observing season for ground-based follow-up observations of the candidates that we're vetting. So I can assure you that we are vetting a lot of candidates. So today I'll talk about some reasons why we need Kepler, and I'll focus principally on processing Kepler data, how we process the data. That's what I'm responsible for on the mission, is to define the algorithms that we use to crunch the data we bring down from the spacecraft to turn the pixels into planets. So I'll talk a little bit about HAP-P7b, about the discoveries that we've announced to the world of new worlds, and we'll look through a bestiary of stellar light curves that enable a whole host of astrophysical investigations, not just exoplanets. So to set the stage, at the bottom left here, there is an image of the Sun taken with the SOHO spacecraft, and superimposed upon that is a silhouette of a giant planet, Jupiter in this case. And so Jupiter, being about a tenth the size of the Sun by radius, blocks about 1% of the area. Now the problem for Kepler is a little bit harder. This is a silhouette of an Earth-sized planet superimposed upon the disk of the Sun. And because the Earth, quite conveniently, is about a tenth the size of Jupiter, we get a % drop in brightness, a part in 10,000, thereabouts. So now the problem is even harder because most of the stars that Kepler looks at are thousands of light years away, and so we can't see the disk, we can't see the silhouette directly. But what we can do is we can monitor the brightness of the star over time, looking for instances where the planet crosses in front of the star just like this and causes a very small drop in brightness. And that's challenging for a whole host of reasons. But the critical questions that Kepler is poised to answer is whether terrestrial planets are common or whether they're rare. What are their sizes and orbital distances from their star? How often do we find these creatures in the habitable zone of their star? That range of distances for which you could find liquid water pooling on the surface. And furthermore, what is their dependence on stellar properties? We don't look simply at solar analogs, twins of the Sun. We look at a full spectrum of main sequence stars, from small M stars, which are about half the size and mass of the Sun, through to late A stars, which are about twice the size of the Sun. So we're interested in what kinds of stars have planets and what kinds of stars have habitable planets. The bottom line, the question we're working towards answering is whether we're alone. If at the end of the mission we find very few or no Earth-like planets in Kepler, then that means that the probability that we're alone, looking out from our vantage point across this immense pool of stars, is very good, that we're alone. But if we find a plethora of Earth-like planets and other planets, then the chances are that there are civilizations out there conducting their own Kepler and SETI searches is much greater. So Kepler forms a stepping stone to other more advanced missions that both NASA and ESA have in mind that will actually do direct imaging and characterization of the atmospheres and surfaces of these planets. Kepler, in some sense, does a census. We determine how far out you have to look to have a really good chance of seeing another Earth and studying it in detail. So here's a transiting extrasolar planet, and what we see with Kepler is that we measure the brightness over time. And for a giant planet like this one, then we can actually see fairly readily the drop in brightness corresponding to when the planet crosses along our line of sight in front of the star. And the observables we have is that we get the depth of the transit, which is indicative of the size of the planet. If you know the size of the star, the fractional drop in brightness is simply the ratio of the area of those two objects. The duration of the transit tells you what velocity the planet has in its orbit about that star. And if you assume that the orbit is circular, then that gives you, together with the mass of the star, you can learn what the inclination is, so what the chord is that the planet's cutting across the disk, and you can get the distance to the planet, which is very interesting because then you can estimate an equilibrium temperature and guess as to whether liquid water might or might not be there. It doesn't tell you that there is water, but it does tell you that it could be there. So these are the first 5 planets that we announced at the beginning of this year. Kepler's 4 through 8b, and here's an artist's rendition of what these planets look like at the inclination angle, the chord at which they're cutting across their star. And you can see that we have a range of different depths depending on the size of the star and the size of the planet. So the smallest one that we've announced so far is Kepler 4b, which is about the size of Neptune. And this would ordinarily be very difficult to find from the ground. We found it in the first 10 days' worth of observations. And these are all short period guys with the longest period about 5 days. And indeed, all of these were found in the first 10 days of observations we collected just over a year ago, right before we went into our nominal science observations. So, in fact, giant planets like this that transit, the transits are so deep they're actually kind of a nuisance. They're a little bit difficult to handle in the pipeline. So, it's a nice problem to have. Now, these are the inferred temperatures and sizes of these guys. Given what we know about the temperature of the star and the size of the star and the distance to the planet, we can estimate the equilibrium temperatures, and we see that a couple of these planets are close enough and hot enough to be above the melting point for iron, and some of them are just about at the melting point for gold. So that's where we are. Now what we're doing is we're pushing down to smaller planets and longer orbital periods as we acquire more data so that you can collect the transits. So here's Kepler 8b. This was our latest planet that we announced. Came in very late in the season because we weren't quite happy with the quality of the radial velocity data. There was a lot of moonlight, and Jeff Marcy wasn't happy. But we noticed that there would be a transit at the last opportunity to observe it with from the ground in radial velocity that before the season ended. And so we conducted observations of the Rosser-McLaughlin effect. And what happens is, as the planet crosses the face of the star is spinning. And so the light on this hemisphere is blue shifted because it's coming towards you, towards us. And the light on this other side, the right-hand side, is red shifted because it's going away from us. So when the planet goes across and blocks a little piece of the star, it's blocking blue shifted light on this side, and when it gets over here, it's blocking red shifted light. Now, if it's going across in the same, basically, if the inclination angle of the orbit is the same as the inclination angle of the spin axis of the star, then you will actually see a symmetric event. But if it's asymmetric, then that indicates there's a tilt between the orbital axis of the planet's orbit and the spin axis of the star, which is indeed the case here. So we estimate that the spin axis to the orbital axis alignment is off by about 26 degrees. And these are the radial velocity measurements we made inside the transit. You can see there's a lot more stuff on this side than there is on the other side. So we can tell that it's a prograde orbit because we're blocking mainly the blue shifted light. Now, we spent $600 million on this mission. Most ground-based telescopes don't cost that much, so you'd expect to get a little bit more for your money here. But actually, the people on the ground are doing an exquisite job, and they're getting near-shot noise-limited performance, but they have to fight the weather and day and night cycle. So the main advantage of Kepler is that it can look at this field of view and collect measurements all the time. Now, what's happening is that the side of the planet that's facing the star is getting heated up, and that's not getting redistributed around the limb very much. And so when the planet sweeps around and goes behind the star, then you get this very small dip, which you can just barely see here. But here on this zoom you can see. So this is about 100 parts per million change in brightness when the light from the planet winks out. So you're seeing the atmosphere of the planet. And what's nice about this result is that the drop in brightness here is about the same size as an Earth-sized planet crossing in front of a sun-like star. So in one fell swoop, yes, this was a planet that had been discovered before Kepler launched, so we put it on our target list. We verified that we can see transiting planets. We saw all 3 transit as soon as we looked at the data. And we also see that we can find small transit-like features that are similar in size and duration to the quarry that we seek, the Holy Grail, Earth-sized planets transiting sun-like stars. I'm learning a lot of interesting astrophysics just by osmosis with all the astrophysicists that are on the team that get so excited about all the data. And the light curves I showed you, first time we showed these light curves to astrophysicists who were visiting from our team, many of them, their jaws dropped, they just gaped as they were watching the screen. And some of them actually drooled, I have to say. And one of our follow-up observers, we sent him some data because we had this very interesting target that was an eclipsing binary, but it looked like there was a third body in the system that was transiting the the components of the eclipsing binary, and it turned out to be a background eclipsing binary on top of a foreground eclipsing binary. But when we sent him the light curve and the finding chart, so he could actually go and make observations with his telescope, he said, please send me the raw data. I don't want to see the smooth data. I don't want to see data that's been doctored. But we had to send him back an email, hey, that is the raw data. We haven't done anything to it. It's just that good. So now I bet you're wondering whether I'm going to announce the detection of any Earth-sized planets out there. Oh, no, I didn't mean to. Well, actually, I can't today. But when we get to the end of the mission, then we hope that this is, at least I personally hope this is the picture that we have of the universe, that it's full of Earth-like planets and other things. So, but even if we don't find this to be the case, if we find no Earth-sized planets, that'll be a very profound result in and of itself. And this mission will be a stunning, dazzling success regardless of which answer we get.